Right, so this is lecture 7, week 4, almost halfway. So far we are learning different techniques of green, at least the background materials. We learned a little bit more about what different pollutants are present in stormwater. Then we learn about the pollutant transport processes. Then we learned a little bit about rainfall, because stormwater, the source of stormwater is rainwater. Rainwater becomes stormwater as soon as it touches the ground. So we interpret a little bit about rainfall, but then next thing is about understanding how much runoff, because that's the stormwater that we wanted to treat. So once we finish those contexts, we kind of know all the background. Then we go to the design mode. So for now, there are still a couple of classes left to learn this background concept, which will be useful for your design. Um, so today we'll have mix of both. One, we'll learn a little bit more about rainfall types, because not all rainfall events are similar. Sometimes, that rainfall can be characterized by intensity, durations, and all that stuff, frequency. But even in the single rainfall, the patterns could change. The intensity could change very differently based on the regions. And those are important to understand, because those will influence how much runoff and how quickly the runoff will appear at the locations. So that's why in the next couple of slides, you'll learn all that. Announcement: office hour are typically on Wednesday at 1 to 2 p.m. But this Wednesday, which is tomorrow, we'll have from 4 to 5 p.m. because I have a workshop till 3 p.m. So that's the reason I wanted to make it postpone it to till 4 to 5 p.m. Again, attending office hour is not mandatory. It's up to you. But I appreciate if you come, and if you have any questions, we do share. We discuss about homework. We discuss about your project. So anything really you can discuss. It's your time to have a talk without worrying about this class and all the other stuff. Homework 3 will be released on Thursday, because there will be 3 to 4 homeworks before midterms. And so this is the homework number 3. That's based on what we are going to cover today and next class. Homework 2, you have submitted. We'll grade it quickly. And I'll also release the solution quickly so that you can also start understanding what you did right or wrong. Quiz 2 will be out on Thursday evening, like every previous quiz. Um, it will be from lecture material 4, 5, 6, and 7. The quiz 1 was from 1, 2, and 3. So everything that was on quiz 1 is not going to be on quiz 2. And everything that is in this class will be part of the quiz. Anything that is in the next class will not be part of the quiz. Again, you have 24 hours window, a little more than 24 hours. It's due by Friday midnight, so you got to take it before then. It's again 2 minutes per question, roughly 10 questions, and there will be 20 minutes. Project, again, I just want to emphasize, you see hypothesis, all that. These are just the guidelines. It's not really that we are emphasizing that you got to have certain hypothesis, because all depends on the type of projects you have. What we really want you guys to do is meet TAs. You got to at least meet me or TA at some time to discuss your projects, because it really helps what you are going to make your projects after the initial discussion, because initially it's all about brainstorming, all that factor. So I really don't penalize anybody for this 5%. As you see, this 5%, 5%, nobody lose that point right now. Partly because I just so that we offer flexibility for your teams to discuss with us and understand. And again, this is your real opportunity for you to learn how to write a report. So the more you meet the TA as well as me, it doesn't really matter. TA is very experienced in this particular area, so that's why you should try to meet TA once you set your topic. But I can help you more in selecting the topic in terms of what specific thing you want to include in your topic. But once that's decided, TA can take over and really help you a lot. So that's why the TA is there to help you learn writing and connecting different pieces together. So I really encourage to email Renan. If you don't know his email ID, so that's Ari Balenka, that's his last name at ucla.edu. Okay, that's the TA. So email him, and he has more flexible time than I have. So that's why I really emphasize meeting him. Because if you email me, I'll meet you, but the time when I can meet will be very specific time on the weeks. Whereas TA, he doesn't have any class, other classes, so that means he can literally meet you most of the working hour. So that's why I say he's very accessible. I should email him, chat with him. He's very also approachable, and I think he can help you a lot. And if you still have any person who is not part of a group, I know that all of you probably found it. And there are some group I know less than 8 students. We could add you. Just don't be alone, because after a point, once you will go to the fifth week, you can't be part of any group. You'll have to do it all your own. The reason is we give you enough time to join a group, and that's usually I understand the challenge of pandemic where you don't meet in person, but at least you should email us or post on campusware that you don't have a group, and then we can put you in some group. So that's all. Again, follow these guidelines as a based on what type of projects you have, but these guidelines can change. For instance, some of you may not have a very specific hypothesis because you have a particular area and you have a specific goal. So it could be a different types of project. But at least we want you to start developing the outline and start putting some text there, and we'll help you on that how the narrative would continue. And I'll also start sharing some news articles where green infrastructure design actually make a big difference in real life. For instance, yesterday I saw one on Instagram because my lab has Instagram account. We follow some of the stormwater projects and other teams, particularly in Los Angeles area. If you wanted to know related to stormwater projects, you should follow LA Sanitations. They do have different types of projects. So in this particular one, I saw a supermarket in Germany. I think that's the original country. Because the supermarkets are huge, they have a big, huge space on the floor, on the usually it's a one story, and then it's a really flat surface. So the entire rooftop they created farming because like 10,000 or 20,000 square feet. So they converted completely into agriculture, and so they put green roof and they harvested different vegetables, and they sell them right there. And what it does, it save them lots of energy because you don't, if you have a green roof, in summer it doesn't get hot. In winter you don't need that much heating bill because it kind of insulated. So these type of real world projects are out there, and so I'll share those examples so that this give you some idea about what you can implement in your projects. For instance, I discussed with Ren a little bit about. I think he was very excited about one of the projects. He discussed how you guys are working on a school, particular school. So I brainstormed with him. What are the different things could be done, and we looked at the Google Earth, and so I suggested something to do. For instance, people can put solar panel in their parking lot, even a small parking lot, and those solar panel usually requires lots of water to remove all the dust, because if you have dust deposited, the efficiency will decrease rapidly because block the sunlight. So those extra water can be come from irrigations, and those irrigated water, once you put on the solar panel, they drain very quickly, so they get wasted usually. But if you put any green infrastructure right below it, those water goes into directly there, so that can irrigate the plant itself. And then as the water percolates through the ground, it can also filter and store again for irrigations. So there are many this kind of interesting design we can incorporate in your projects, particularly in school project. Whereas we can look at both energy as well as water aspect. And the nice thing about this kind of projects, you can be part of a competition, EPA competitions, which was released yesterday. Obviously, UCLA, we didn't submit last year or anything. So University of Pennsylvania, they got the first prize this time. And they kind of followed what we did a year before, because our team won the first prize the year before. So I kind of, again, it has to be led by undergrad students and some grad students, mostly undergrad. So if you are already doing this one, it's very easy to convert that to a winnable team. So I really encourage you to contact with your TAs, and at least, whether you do be part of a competition or not, you can at least, think of what can be done, imaginary way. So anything you do now can help you compete in October. It's really, very simple thing. Once you have done your report, it's very easy to, you can see it for a couple of weeks and convert that to a competitive draft for the competitions. And also you win prize, it's, I think it's almost $5,000 for the team. So if you are, let's say, team of 5 students, you each get $1,000. So it has monetary benefit. You will be highlighted by the Congress in, yeah, I mean, Congress, I mean, the constituency. So the congressmen, they will get also letters that UCLA got it. So there are a lot of, highlight for that award. And I know for sure if we apply, we'll get it, because we do research on that a lot. So we can bring you that innovations which you need. So it's called. Let me send you the link right now. So it's called Rain EPA Rainwater Challenge. Okay, Rainwork Challenge. So let me see. I'll post the link also on the campusware, but now I post the link here. You can go that right now. It is winners as announced yesterday. As you can see, master plan. There are two categories. One is demonstration project. Another is master plan. I mean, both are very similar. We got demonstration project first prize the year before. As I said, because we teach this class and we have a lot of time to prepare for it, I, as I said, and I have done it once, and it's very easy to get award. We just have to convert your one of your projects into a report. It will be more visual, less writing, but just because you wrote the report, it will be much more easier. And also, it doesn't have to be just civil engineering. Usually, they encourage to have group of students from environmental engineering, architecture, a different group, urban planning. Then only it makes it looks nice, but still fine. If you have a very good report, they will give you. Again, this is the benefit of being in this class, will help you prepare for that. All right, so enough of this, things that we have been talking. All I'm trying to say is focus on your report or the projects that will give you real world experience, and it has a lot of more benefit than you can imagine. Um, these are things is like now in your resume, it looks so great, for grad school applications or even industry job, everything, that just give you a different edge. Um, all right, so that's for the report, and again discuss with Brennan. So the class objective, I remember that intensity, durations, and frequency method, or the curve. Uh, um, that one we kind of over skimmed through it very quickly. So I wanted to just revisit again. And today we are going to learn a little bit more about hydrograph. Hydrograph means how the rainfall patterns evolve. As I said, each rainfall is the cause for the runoff that is going to be created. So that means the types of rainfall, the patterns of rainfall, the intensity, how it changes with time. It's all going to influence the type of the amount of runoff created at a site. So that means we got to have understanding of type of rainfall that receive in different area. Now, if you are comparing the effect of rainfall at different locations, you got to normalize the rainfall. Now that means you have to say that what how I can make the same rainfall at different locations so that we can simulate the effect. That's why unit hydrograph is a powerful techniques to do that. Change all rainfall into certain normalized ways. So we'll learn that. We'll also learn the concept of design. I think the third one is not concepts of design storm. Yes, yes. So as I said, green infrastructure is designed based on a specific rainfall as assumption. For instance, for Los Angeles, we say 85 percentile rainfall. You learn that. What does that mean? It means all the rainfall that received historically in this area, 85% of the rainfall will be captured in this green infrastructure design. Anything that other 50 percentile will just too expensive to build because those are heavy intensity rainfall. You learn about hydrograph, which is the runoff models, and we'll learn about how to estimate the peak flow or the highest amount of runoff you can receive at a point, because that will determine whether your system will be flooded completely or it will not be have any flooding. There are many methods. So NRCS method is something that people have been using. That's the USGS method. We'll not have time for that. I will learn that next class, but at least you'll learn the concept. We have that time. All right. So we covered that very quickly last year. The concept. I just want to have a poll just to see if you understand the basic an idea of 10-year rainfall and 100-year rainfall. What's that difference means even? So there is a poll between 10 years and 100-year rainfall events, which event is more likely to cause flooding? Means I'm asking, a 100-year rainfall will have more heavy rainfall or light rainfall? Which one will be high intensity rainfall? Or think of this way. Anyway, I'm not going to speak anything. Next 30 seconds, you have time to answer these questions. You have choice A, 10 years, choice B, 100 years. Okay, 88% voted. Once it's more than 90, I'm pretty satisfied. But you should all vote, because vote means select your options, whether you understand it or not, because you get some thinking, and that will help you answer your quiz questions. All right, I'm going to end the poll and share the result. So the answer is 100 years. That's the reason is, the if you increase the the frequency or the duration, you say that in 100 years you are more likely to receive a rainfall that is very high intensity than in 10 years. So the longer you wait, the more likely one of those rainfall will be very heavy. So 100-year rainfall events means, it just means that comes in once in 100 years. So that must be very extreme. And so that's why it can create the flooding more likely than um, 1 year rainfall. So the difference is intensity. Okay, high intensity rainfalls are less frequent. So that's why intensity duration frequency curve is designed, and for every location there is a data. And the reason I want you guys to use this web links to um, look for the uh, so what I'm going to do is I'm going to put the web link in the chat window. I want you guys to try this instead of me showing you how to do it. So let me copy in the chat window so that you can go to that link, and then go to this link. Let's see if it is still working, because sometimes I found that it's um, so copy the link and go to the web page. Okay, it's working. So now go to your hometown zip code, or if you can select, let's say you are from California, select California, and then it will open a new Windows. You know what? Let me share the screen. Stop sharing. Um, I'm going to share a new screen so that you can see what I'm doing, but you should do on your own because I share a link with you. So this is what I see. But now you should all do different things. Means you should go to your own hometown, or at least the place you want to check, because this is relevant for US. So unfortunately, if you are from different country, this is just example. So let's say I'm going to California and I want to go to UCLA. Okay, so how should I do it? Obviously, you can look for station, or you can just search for address. Let me search 90095. That's UCLA zip code. So I just click on that. So as you see, it goes there. So that's good. So if you want to see different station, or you can move crosswire, that's fine. But if you see, look at the station, it tell you where exactly they are collecting data all the time. So these are different station. There is right inside the inside UCLA there is a map. So based on that, you receive this rainfall data. So if you scroll down, this is the intensity duration data. The the columns are different. I think um, frequency, 50-year interval. So 1 year, 2 year intervals, 5 year intervals, 10-year intervals. So that's the frequency. 200 and 1,000 years. So it's pretty long time. And then the x-axis, or the columns or the rows, are different durations. So let's say I'm going to pick this one. What does that mean? It means that this is the rainfall intensity you are expected to receive if you are looking for 10-year rainfall events lasting 60 minutes. So you are looking for what is the rainfall intensity would be if it goes for 1 hour, and it comes every 10 years once. So that's the one. This is in inch, by the way. You can change it to different scale. Um, so you see there are different things you can show here, and you can also go to the graph. It shows the graphically, it says the exact same data. For instance, if I ask you these questions, what is the rainfall intensity or the depth for a 24-hour event and 100-year rainfall? So you go to look for 24 hours, which is here. Um, let me see if I can show you a kind of a pointer. I forgot how to show the pointer, but again, so look for 24 hours here on the x-axis, and then if you see 100-year rainfall, which is blue, it meet around this 10-inch, little less than 10-inch depth. And you can always go back into tabular mode and you can check that. So 100-year rainfall events and 24 hours, which is this. It goes around 8.31 inch. So this is the rainfall intensity that you want to take it from that, and use it for your designed runoff calculations. So this website you will be using for any site you choose for your projects. This is where you can get the intensity duration frequency curve. So I hope now that you know how to use it online. So I'm going to stop sharing. And I hope all you tried on your own for your hometown or home places, or any places in US, so that you know how to do it. Any difficulties while you are doing that? Okay, good. So at least one skill you learned that always going to use when they ask you where to find those informations. Okay, so let's see. And these are the questions they will ask. If you go for stormwater treatment design in LF Department of Sanitation, this is what the question they will ask. What is intensity duration? They are more theoretical compared to company. Company don't care about how much your knowledge is. They look for your attitude. But if you go for this government agency, they have these standard questions. They will ask you. They will ask you attitude questions, but mostly they will also test you for your background. Um, so it's good to at least have some understanding of stormwater related jargons. All right, so this is again just a question. I just example I did it. So this is what copied, so you can see how it looks like. So a lot of times, if you know a duration of rainfall, you can or depth, you can change it to per hour. For instance, this is example given if you are given 5 minute durations and the intense depth was zero point 0.3 inch. I ask you what is the depth would be if it is rain for 1 hour. So it's very simple, you just divide per minute times 60. So same thing here. If you do the next one, you are given only 15 minutes rainfall intensity or depth, and I ask you if you convert that to intensity inch per hour, then you obviously change 0.574 in 15 minutes, and you know that 1 hour is 60 minutes. So basically 4 times 0.574. So whatever that, it will be inch per hour. So you can convert that like this for a lot of other factors if you know one values. So now, as you see, in all these cases, we get a single number, rainfall intensity. So, but you know that most of the time in rainfall, engineers or scientists, they know that the rainfall intensity is not constant. Even you go outside when the rain started, initially maybe it's heavy rainfall, then it slow down. So how do you use just a single intensity to design something? It is going to be accurate. So that's why you have to know at what time you have to use a single intensity versus the distributions. So that's what the next slide is about. So single intensity will give you a design that will tell you what's the maximum amount of runoff you may receive at that point. So that determines the peak discharge. Peak discharge means maximum volume of stormwater. So that's related to flooding. Okay, because as you know, the primary function of green infrastructure is reduce flooding. So that means you have to think of the worst case scenario. Worst case scenario means what's the rainfall maximum rainfall intensity, and for that rainfall intensity, what could be the corresponding runoff volume. So that's why single intensity is useful to determine the peak discharge. So that's remember that one aspect of it. This could be a potential quiz questions when single intensity is useful. But you should know that it doesn't tell anything about how quickly that peak will arrive at that spot, because for that it depends on how long the rainfall has been happening. What's the distribution of rainfall, all that. So it doesn't say anything about the speed, or the how fast the peak will appear at certain monitoring point or at your locations of your green infrastructures. So that's why distribution method, distribution of rainfall is more important for those kind of condition where you want to determine the size, and all the other aspect of it. And for that, you need this SCS other method, or the one I talk about, which we'll discuss next time. But so just know the difference. You need both. But one thing will give you certain things, which is easy to do, is peak, but distribution will give you something else. But then the other thing is, when you compare or design green infrastructures, these are designed for certain rainfall events. So if you, let's say somebody designed a rainfall events in a New York, how do you compare that with California? Because it does have a very different rainfall. Because all you see is you measure the runoff volume, right? So all you're doing is a flow rate at that locations, and but each one respond to different types of rainfall. So when you are comparing how your system is respond to different rainfall, you have to somehow normalize that rainfall type. So what it does, it based on whatever the rainfall distribution you have, you change to unit hydrograph. Hydrograph means related to rainfall distributions. So we'll talk about that. So unit hydrograph means it assume that you got unit rainfall, means 1 inch or 1 millimeters or 1 centimeter. Doesn't matter. You decide that. Okay, so it says the um, maximum rainfall at that location has to be 1 inch. Okay, and so that means if you have more than 1 inch, you normalize that to 1 inch. So that means you divide your peak, uh, your all rainfall time to divided by the maximum intensity for that locations to get the unit hydrograph. So again, I'll share a document so that you can see its steps, but I'll just give you the concept behind it. So again, unit hydrograph means 1 inch or 1 centimeter or whatever the units you decide. That's the maximum intensity. That's all it means. And the duration is also fixed. It assumes that it has 24 hours. Um, it not more than 24 hours. So once you set these conditions, any type of rainfall you can convert them to these distributions. So we'll show how to do it. But just know those two concepts: 24 hours and single unit intensity. But now, just example I'm showing you here. This is, let's say this is a rainfall. What you saw over here is this is the depth at different time. So at different time, initially it was very small rainfall, then suddenly it's peak, it's rising, and suddenly it rain a lot to 1 inch after a certain time, and then it fall down quickly, and then it goes. So if you do cumulative depth, basically add them together, it's rising, and then you see this. So this one is called cumulative depth of incremental rainfall depth. Okay, and that distributions will also tell you what type of rainfall it is, and it tells a little bit more about how you should design the rainfall of the green infrastructures. So this is an example I'm showing you. There are different types of rainfall you can think of. One is orally peaking. Orally peaking means the highest rainfall intensity shows up orally during rainfall. So at the start of rain, it is usually heavy, then it becomes slower and slower. Then the second one is more like a normal distributions. Central peaking means initially it's slow, then it peak over here, and then it goes down. And the third one is like initially it was slow flow rate, and then or the slow rainfall intensity, it peaks towards the end. So these are the three different ways you can describe the rainfall distributions at different locations. Each one has its consequence, because if you are looking for the first one, you know that your most flooding will happen the very early. Okay, and so that means your design will be in correspond to that. If you are looking for the other one, initial rainfall will be mostly, you will not have any runoff. It will only, because it's very slow flow rate, and the later runoff will be much higher. So these are all influencing the design to some extent. Uh, so why unit hydrograph is again useful, because you can now compare your hydrograph distribution to your runoff distributions. That way you can calculate how long before you have time the flooding to appear. So that's we call lag time, all that. So we'll discuss that. So this is just example I'm giving. This will explain visually what that means. So you have in this graph, you have time on the x-axis, y-axis, you have two things, either rainfall intensity or you have the stream discharge rate or the runoff. So either rainfall or runoff. The blue bar you see over here is the rainfall. So this is rainfall. And the gray bar over here you see, or the purple color is runoff or stormwater at locations. So now if you have these two graph together, then you know that when it rains this much amount initially, it corresponds to this much flow rate at the locations, at certain places. So if you look at the center of the rainfall event, so which is here, and the center of the centroid of the runoff events, then the difference is called lag time. Lag time means how long before the peak appears. Okay. So this lag time is very important because your goal is to increase that lag time a lot more. Or this is one thing you probably realized during COVID. A lot of time they call flatten the peak. This is exactly same thing. The concept it came from hydrology. So here what we are doing here is if you have lots of green infrastructure, you are flattening the peak, means your peak flow rate will be so small that it's not going to create this flooding. And not only that, it slowed down the flow rate, at this later time. So that means you have more time to respond to flooding. That means you can have a early warning for flooding. That means people are now ready to do all the preventive actions. For instance, if you are creating a dam, you can say that open the dam gate because now we are going to receive a lot of runoff. So these are different design factors, and this also shows how to take different preventive actions. So that all depends on your rainfall distribution data, and so that's why it's very important to have this unit hydrograph so that you can compare the runoff at different locations in response to that unit hydrograph. So you should know that this graph should be in your mind all the time. You should know what is the lag time, what is the peak means. Graphically you should be able to show that. This is one of the midterm questions always I put just to describe um, this graph. So I have somebody raise hand. Kathy, do you have a question?
Yeah, I was wondering. So, is the bar graph in this plot the hydrograph?
Yes.
Okay, and then the line graph is the hydrograph.
Yes.
Okay, and then the so I thought it was a time difference between the peak of the hydrograph and hydrograph, but isn't where that black line is, um, like not the peak?
So yes, that's they assume, yes, the peak. This black line is the near the peak. Okay, and this line is towards the center of the rainfall events.
Okay, so that line should be where the center of the rainfall event is.
Yeah.
Okay,
Yes.
okay, that makes sense. Thank you.
So it is like kind of confusing here, but if imagine this is the hydrograph is this, then you say this is the center. Um, so again, a lot of times it's very difficult to know the center because you don't know how long it has been raining. So there are some assumption involved when you decide what the center would be. Because but again, that's at the end. So when you have a rainfall, you take out the rainfall distribution data and then you create that assumptions.
Okay, thank you.
All right.
Wait,
So
Professor?
yeah,
So basically what you mean is that we don't if we were given a hydrograph
yeah,
overlaps with the hydrograph as
yeah.
like one graph on the test, then how would we know the like where the center is if we because usually we just look at where the highest point is for the peak, but
Yeah.
now you're saying we need to find the center. So
Let me
that's a little bit harder. That's just like a bit of like guesstimating.
let me give a hypothetical question that we can learn. So let's say this is my lines are pretty great. Okay, so this is a axis. This is time, and let's say I say this is the rainfall data. Okay, what it means that you have a rainfall intensity. It start and I just create a square or circle, the rectangle, whatever you may call. So this is the rainfall data. So at certain time t equal to 0, t0, it start raining, and this is delta t, and so this is t plus delta t. Okay, t0 for delta t. Delta t is the duration time it rain. So this is, let's say, hydrograph rainfall data. It's just pretty flat. Okay, so it's not ideal, but let's say this is the example questions or quiz questions. And then I say that, okay, you have now in response to that, you will have a rainfall or the runoff data. So it will be like, let's say this is the runoff data. And I ask you, what is the lag time? Okay, usually there are time will be given here. These are all, let's say this is 1 minute. This is 10 minute. This is, let's say, 25 minute. Nothing to scale, but I'm just saying that this is the. So then if based on the information given, I ask you what is the lag time. Okay, so you'll know that the lag time is the difference between the peak to the center of the location. So this is 1 minute, this is 10 minutes. So the center must be 1/10 minus 1 divided by 2. So it will be how much? 10 divided by 1 is 9. Divided by 2 is 4.5. So that the width is 9. So that means exactly half over here. So that means 1 plus 4.5 would be, this is 5.5 time. And this is 25 minutes. So the lag time would be difference between this. So that will be 25 minute minus 5.5 minute. So that will be 19.5 minutes. So that means you have 19.5 minutes to before the flooding will occur, or at least the peak flow will occur. Whether that will cause flooding or not, that depends on the system that you have in place in the downstream. Does it make sense?
So what if the hydrograph's not flat? Would we just be taking the average between T
Yeah,
naught?
you'll just identify. Say, I assume that. Let's say I give you like this.
So it's always, we just choose a midpoint every time.
Yeah, you can decide. Usually you do the centroid. That's the weighted curve. But if you can't, graph wise you cannot find, just pick any location and say this is the center.
Okay, got it. Thanks.
Usually, that's the definition wise. What is that means in when the 50% of the total rain is delivered. Okay, that's the volume. So centroid means that. It means that when after 50% of the rainfall is delivered, then only you call that, that's the middle time. All right, so I will go to the next slide. Um, so now that you know what is unit hydrograph, there are different types of hydrograph based on where you are from. Different region has those, as you said, that this is the cumulative one, and that shape can vary from where you are from, and that will determine by this. Okay, either early picking or the central picking or the late picking. That will make the shape look very different. For instance, if it's early picking, things will rise very quickly first, then it will not rise because initially you are very much rainfall. So this is early picking, and this is late picking, and the in between would be the central picking. So by just looking at the shape, you can tell whether it's early picking or not based on when it shows up early. So that's how it is defined. Different type of type 1 way. This is just defined. Okay. So as you see, if you know this type of curve, you can always convert that to unit hydrograph. That's the one thing you will learn. But just different region, you can see type 1 is here. So this is, if you see the image clearly, so that's Los Angeles will be type 1. So Alaska, Los Angeles, this is type 1. Type 2 would be more like a Seattle area, or this is type 2, or type 1A. Sorry, it's type 1A. And then if you look at the rest of the area, this is anything white is type, this is more common, type 2. Any white area, and then Texas, a little bit Texas and New Orleans, that will be type 3. So what it means that it's already tell you what kind of patterns you have. If you know the patterns, you can always use the patterns on the distributions to calculate your unit hydrograph. Now something will give you example. That's I will know. All right. So now that I told you how to discuss whether um, type of graphs, whether early picking or not based on the shape. Let's see if you can guess this answer. There's a question on chat window from Andrew. I'll answer that after this quiz. Which type of region has early rainfall peaks? Type 1, type 1A, type 2, type 3. I'll show you example here based on how I. So as you see, if it's early picking, you'll think full slope orally. Okay. If it is late picking, that will be flattened in the beginning. Okay. I do have 20 more seconds to answer this before I stop the. 10 more seconds. Okay, so I'll stop the poll. All right, so I share the result. Let's see what is early picking. Early picking means, if you have high intensity at the beginning, they will rise very quickly. So this, out of all of them, this is the one which rise very quickly in the beginning. That means it must have early high intensity rainfall. Otherwise, Y cumulative mass will be higher initially. So that's why this is the earliest. So that's the answer would be type 1A. All right, so at least you now know how to look for examples. So now the example is developing a design storm hydrograph from CSP distribution curve. So this is the examples I have recorded before, so I will not do that in this class. I'll just ask you to watch that, and I'll share the Excel file so that you can try that at home, just for that, because it's part of the example problem I created. I share the Excel file. So if you have difficulty, ask on the campusware. So this is again recorded before, so I will not do this one so that you know. The last thing I want to say about this rainfall patterns is for Los Angeles. If you are doing a project related to Los Angeles, their stormwater guideline says that you have to consider 85th percentile 24 hours rainfall events or 0.75 inch events for standard urban stormwater mitigation plan, whichever you want to choose. So as you see this, for Los Angeles, the 24-hour rainfall events could vary, different intensity based on whether 100-year events or all that. Because it doesn't rain much, it considers 0.75 inch as our standard. So you are assuming 0.7 inch for entire 24 hours rainfall. Then you are designing all your BMP to treat this stormwater. So 85 percentile rainfall. Otherwise, if you look for 85 percentile, that rainfall intensity could vary between 0.3 to 1.5 inch, depend on which location you are in the LA County. Some receive more rainfall than other. So in this link, you can check that. But just know that if somebody asks this question, what's the design storm events? You are talking about 85 percentile storm events, 24-hour storm event. So it means that if you take 24-hour rainfall events in Los Angeles and any site for last 100 years, the intensity correspond to which every rainfall events are either less than 85 percentage of the rainfall events, then that's the rainfall intensity we'll use. And again, this varies from that IDF curve. You can go back and check there and find their answers for different locations. All right, so Andrew's question was, can seasonal change affect rainfall distribution in an area? Yes, the shape will not change. Okay, that's related to climate in that area and how the precipitation occurs. But the rainfall intensity obviously will change, but the shape, whether it appears early or later, will not change. Um, all right, it's not next class, after break. All right, so we have a 10-minute break. We'll meet at 5:05, and we'll discuss about runoff estimations. Again, the slides I skipped, I'll post the video, or it's already there from last year video, so I'll share that playlist so that you can check. Okay, so we'll meet at 5:05. I'm going to pause recording. Okay, so before the class, before the break, we discussed about rainfall. Now it's more about runoff because that's what the whole design for green infrastructures is. And another thing I want to say is that start working on your project because these are the things you are going to directly apply, and that's where you are going to learn a lot. The concept, the theory, or the math of green infrastructure design is very simple. It's really not that complicated. So that's why you learn a lot when you are designing things. That's where you want to learn. For instance, this equation, we learned that probably in, I don't remember, maybe in CEE153, but if not, definitely CEE150, if you have, but it's a simple concept. It's saying that how much runoff volumes we create at a locations is proportional to how much rainfall it receives and how much area that it captures the rainfall. And so that's the whole idea, that's basically you're pouring all the water. And then there is a function C, which is a runoff coefficient, something that we discussed few slides ago, not to this class, but before this class, that everywhere the rainfall that you receive is not going to become runoff because some of them will be runoff, some of them will infiltrate into ground, a fraction of them will be evaporated, a fraction of them will be stuck in the tree canopy as abstractions. Some of them will also get stuck in the ponds and all those other area where they can capture water. And also we are using humans are using the we are draw down we pump water, so you use water all the time. So that means whatever rainfall happen, not all of them will become runoff, only a fraction of them. And what of that fraction, it depends on the location or the geography or the site properties, such as impervious surface. If you have impervious surface, it limit the infiltration, that means more become runoff. If you have a slopey area, like that means higher slope, every raindrop it receive, it very less likely to infiltrate before it drain into another locations. So because of that reason, the C is a function of the location characteristic, and your goal is to find that C. So those are the things we are going to learn in this next couple of slides. So these are the learning assessment questions, something that you should be able to answer. You should say, what's the identify three land characteristics that decrease runoff? As I said, impervious surface, anything that can change the amount of rainfall that leave the system. Now, these are all things you discuss, but let's get to the runoff. So again, why we are doing it, why engineers do it, why scientists do it, is because you want to treat that runoff, to harvest that water, or you want to treat that runoff or get rid of that runoff quickly so that it doesn't become flooded. So that runoff volume is very important, and you should know how much you want to treat. And so again, as I said, the runoff will depends on many factors. Rainfall, that's the input source. Loss means how much of that input leave the system because of infiltrations, evapotranspirations, or abstractions. And it also depends on how quickly it being moved from one location to another, or conveyance. That depends on the impervious surface as well as the slope and other factors, or the friction that the land will exert on that flow of water. That's why if you have a grassy area, it soak a lot of water before it flow. But if you that same raindrop goes to your parking lots, that become runoff quickly because it has less friction to store it. And then also you learn how to calculate the time to get the peak flow, because that's important. That will be the warning systems. Now, anytime there is a rainfall happen, that flash flood warning is based on this, that wall set characteristic. So that's what you are going to learn. So again, as I said, we learned that rainfall intensity, it could vary based on the frequency of rainfall events, 100-year event, 10-year events. But this is just a way to remember what rainfall intensity is pretty bad. Less than half inch is more frequent most of the time. It doesn't create much runoff. It will just soak the water. You will not have any problems. Um, zero point 0.1, 0.5 to 1.5 inch intensity will create most of the runoff in most of the locations. Obviously, in urban area, I'm talking about. In agriculture, in the natural place where you have lots of tree, it may not create much. I mean, it will create runoff, but it will not make any damage. 1.5 to 3 inch rainfall, if it receive at any location, is pretty bad. It is bad enough to create a lot of flooding because you'll have lots of water moving very fast. Anytime we become more than 3 inch rainfall, it's called extreme rainfall events. It's usually very unlikely. It happens when if you have hurricane or that factor. Imagine entire area you'll have 3 inch, this much water, somebody dump it. It has to move very quickly, So that's the reason all flooding happens.
Professor,
Yes,
so is this inch per hour?
yes.
Okay.
It's a the inch per hour, or usually a lot of times people say the depth. Even it doesn't happen within an hour, but even that much rainfall happens is pretty bad.
But
Obviously, not more, many days.
rainfall intensity itself, the unit of measurement is like length over time, right?
Yes, yes, yes.
Okay.
So I think in this context, it's mostly on a depth. At any single rainfall event, how much rainfall happens. So let's say
Okay.
this 3 inch rainfall happens not in 30 minutes. It's pretty bad already, right? So that 3 inch rainfall continuously happen for 2 hours is also bad because that's it is this much water is being dumped. Um, so this is mostly a cumulative depth in that one rainfall event in this particular case. Even though I wrote rainfall intensity here. Um, hydrograph, again, we go back to the main point that we discussed. The lag times are important. And even though that time I said the peak is the factors, as I said, peak is very hard to determine because you can measure it because that depends on how frequently we are taking samples. So practically, it's always the center of mass. Okay, so if your rainfall distribution, the runoff is like a binomial curve, then the peak coincide with the center of mass. Okay, so that's why this is peak and this is center of mass. Um, okay, so they coincide in the, but if your rainfall is like this, your center of mass will be shift towards a little bit right. Okay, so this is the center of mass. And again, peak you can measure all the time. So always if all the difference between center of mass between the discharge and rainfall is your hydrograph. But if I draw something like and in that particular case, I draw more like a, let me go back, that graph. Yeah. So because I draw the graph more like a uniform distribution, so it's in this case, you can take peak is very easy. But if you want to determine the lag time, if the shape is different, you always look for center of mass. That's basically you are saying when the 50% of the water delivered as a rainfall, the time it takes for the 50% water to become as part of runoff. So that difference is the lag time. So that 50% is the center of mass. So that's what it says here because different shapes are there. So I just want to highlight the definitions because in real world, the center of mass will be always shifted from the peak flow. It depends on the slope and many other factors. Um, so by definition, look at these slides more often, like when you talk about lag time. There is another factor is the time of concentrations. Time of concentration means how long all the storm water, because that determine the highest amount of flow rate, but I'll get to that next. But this is the figure here. So lag time, as you see, this is rainfall. The difference between center of mass and center of mass is lag time. Okay. Whereas the time of concentration means how, what time of concentration in a conceptual, what is that means is the longest time it takes for a rainwater to travel from uh, a location in the collection area to the monitoring area. So that's the time of concentration. So it's the longest time. Okay. So how do you determine this one? So basically you are saying when the rain stop and the time from when the rain stop to all the point of inflection. Point of inflection means where the you can clearly measure the things are decreasing very rapidly. Okay. So point of inflection is basically at the if you take the derivative, that's where the slope change. If you take the second derivative of this one, so that's the point of inflection here, and the distance between the when the rain stop. So that's the time of concentrations. But theoretically or conceptually, it means the longest time a raindrop can travel from a location. For instance, let me make a um, simple graph. Okay, so let's say this is watershed area. Okay, and you are collecting water here, this point. So when there is a raindrop happens, it can raindrop any locations. Let's say throwing a, I'm just saying that this is how water flow. I'm just making a different tributary, all that stuffs. Okay. So let's say this is time from here to here is 10 minutes. This is 5 minutes from here to here. From here to here is 5. This is 20. This is, I'm just throwing a random number, okay? So that way you know. So this gap is, this is the time it takes between those points. So if I say what is the time of concentration, you basically say that what's the longest time the water will take to move from one location to that. And it means that during the entire time, every raindrop happens, you will not see there, but it's all being in that system, within the system. And you'll take that much time to leave the system. So that time of concentration will be longest time. That means 10 TC over here will be 10 plus 5 plus 5. So I'm just picking 10 plus 5 plus 5, then um, plus 20 for this line. If I draw this line, this is the, okay, so this is the this. But if you do alternative way, you don't know exactly whether this is the maximum time. So let's add up another one. So this is 10 plus 5, so 10 plus 5 plus 5. And then if you add 5 plus 7, this is not more than 20. So that means that's not. And then this plus 5, then another 25 here. So that would be, so this will be 25 plus 30, then 40, 50. This is 50 minutes. This is 2. So this, let's say 20, 30, 40. So that means if the raindrop take this path or the runoff, it takes around 40 minutes. But if it goes from this path, it takes 50 minutes. So time of concentration for this particular collection of watershed is 50 minutes. That means it takes 50 minutes. Within that 50 minutes, every rainfall happens. This should all show up in that one location at that spot. So this is what fundamentally we call time of concentrations. And so your goal, what is the time of concentration depend on? It depends on the obviously length scale. That's what I show you. It also depends on the slope. Slope means, if you have a higher slope, time of concentration will decrease because it will rapidly move from locations. And then also it depends on the roughness or the things that can slow down, like green infrastructures. So your goal as a green infrastructure design is to decrease that or increase that time of concentrations. When you increase that one, the peak will slow. That's the whole call. That's the whole thing called flattening the curve. So if your design at that location is such a way that your time of concentration is very long, then obviously it will be a good design. So just know these things. This is relevant for quiz. Okay. Um, this is again visually to show that when you talk about lag time, you are looking for the center distance to center of mass. But when you're looking for lag time or the time of concentrations, you are looking for end of the rainfall to the point of inflections. Okay. Point of inflection means again if you take the derivative of the slope here, wherever the slope directions and the receding curves change. So this is decreasing and then suddenly it will the point, double derivative or something. All right, so time of concentration, there are many ways to calculate it. As I said, it depends on the length, it depends on the slope. Slope means S, okay, and L is the length of that flow path. And then it depends on the surface roughness, basically how much impervious surface, all that, which is N. So if you know these three numbers, there are many empirical equation you can use. So these are the five, there are many methods I listed here. So your company, when you join or you, particularly if you calculate ST and it's given for your locations or word set, you can calculate based on all these values. So you can choose any of them. It has its own advantage and disadvantage written here. Again, I'll share this handout so that you know more for use for your project. So the now question is why we need this all this for your design project, because you want to know what's the peak flow. Because time of imagine if your rainfall happen longer than the time of concentration, that means you are going to get the very high flow rate. Once the rainfall happens more than the time of concentration, the flow rate will not change anymore because every drop that drop there is also already exit the system. It's not concentrating anymore. It's the same thing. So that's just the reason why we use it. So going back, the way to get the peak flow is the rational method, which is which means that flow rate depends on the intensity times area. So this is one intensity that you are. This is where you are assuming, and this phi value is runoff coefficient. This is something depends on the how impervious or the surface type property, and this is something is already given to you as a table, and you just pick that number based on how much percentage impervious, all that you can assume certain C value, and those are the things given here. So as you see, if a business area with a downtown area, this is like C value is 70 to 95. That means 95% of all rainfall becomes runoff. That's the highest. As you go residential area, it decreases. Single family residential area, the runoff coefficient is 30 to 50%. What that means is because you expect there will be lawn, there will be all the other trees and stuffs that will capture that runoff. That's why you don't have that high amount of rainfall or the runoff. But if you look at industrial area, it can be 60 to 90% again because of the fact that it has more impervious surface. But another thing you can check if your park, if you have lots very less impervious surface, that's why only 10 to 25% become runoff. So again, these are all given to you. The source is here. So that means you can assume your C value for your project based on the locations you have and use this table. And the area you can, how much catchment area that you can determine by using Google. So let's say you are using school. One of the project is school. So you can draw a line in a Google Earth around it and it will tell you what's the area when you make that shape. Or you can use GIS map. And Google Earth can also tell you which side it will drain into because it also gives you some elevations. You can also estimate the runoff intensity or design storm based on IDF curve, something that I already show you, and the C value from this table. And then you just use this area the formula to calculate how much runoff will generate at your property. So now that you have a site, you can go back and exactly do this one and write already in your report. So for instance, you go to Google Earth, calculate the area for your site if you have already chosen. C value, this is already given to you. You can assume something and you write that value. And rainfall intensity, you know the map or that for that website that I show you, get that one. So now this calculation on one paragraph is already written or done for your site if you have a site. All right, so that's all in terms of how to create calculate the peak flow or runoff very quickly. Then we have more complex method how to do those based on distribution everything. So, but we'll not do that today. We'll do that next class. I want to dedicate the at least the last 20 minutes of today to discuss about any projects or any questions you may have. But other than that, we are done for the class today as far as new materials. So everything until now will be part of the quiz. This will be next class. Okay. All right. So do you have any question that you want this to be part of recording? All right. I'm going to stop the recording.